Good evening, everyone. So, today we reached week 11 of our doubt and problem solving session in the course of. Hello, 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 hello.
Hello.
Am I audible?
Yes, sir. You are audible.
Okay, so shall we begin?
Sir, I'm not a student. I'm from NPTEL. I came to monitor this session, sir.
Oh, okay. Actually, I was waiting for a student, so I thought to. Okay, okay, fine. So, you
Oh,
will be here?
no, sir. I just came to monitor this session. That's it, sir.
Okay, okay. So, oh, I thought you are a student, so I was waiting. So, okay, it's fine.
No, no. We have been advised to like randomly monitor these sessions.
Okay, 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 fine. So, can I go ahead?
Yes, sir. Please.
Okay, I was actually teaching, so I thought some student entered.
Okay. I'm sorry to interrupt you.
No, no, it's fine. That's completely okay. Okay, so okay, so in this week, mainly we are dealing with the character. Till now, what we have seen is enough of manufacturing and the application purpose of the carbon materials. That different types of carbon materials, such as graphene, graphite, as well as carbon nanotube. How can we scale up to the industry level and the various characterizations? But here in this lectures, mainly we will be seeing that because in any for any material it is very important to see in the lab scale that how it is in a lab scale how it can be performed. So for the lab skills, in order to know that your material is pure and what are this morphology, surface morphology, what are these characteristics, characteristics means to say the material characteristics. You can also find some electrical and mechanical properties of your material. So one of the very well known property of your of any material, that in order to see the quality, is the X-ray diffraction. Okay, so in the short form of the X-ray diffraction is your XRD. Okay, so as you can see here, the X-rays wavelength are in the range of interatomic distance in this case. Okay, so interatomic distance. So do you know what is interatomic distance? So let's say if you take any material and here is the layer of your material. Okay, in your material there will be a different. Let me take my. Uh, Yeah, so this is suppose the layer. Okay, so atoms are arranged in this particular manner in the layer. So the distance between these two layer is nothing but the interlayer. So this is talking about this interatomic layer. Okay, interatomic distance is how much? 0.5 to 2.5 angstrom. Okay, so there is lambda is the wavelength of your X-ray. Okay, so here as you can see the schematic, or you can see the pictorial of how it can work, that I will explain also. And we have some questions, numerical questions after this, that we are going to solve, that will be helpful for your assignments. So this term diffraction and scattering are often interchangeably used. Scattering occurs in the direction while diffraction is specific direction. Okay, so here you have often heard this two terms. First one is your scattering. Okay, we have also learned that how the scattering takes place when we were studying our different characteristics. But here the term diffraction. So what is diffraction? Okay, and how in the XRD diffraction is taking place. Okay, so here when incident rays. Okay, so suppose your X-ray. I have also told you that how the X-ray is generated. So suppose your material is here. So incident X-ray will come to your material and that will diffract. Okay, this is your incident and this is your diffracted from the sample, undergo constructive interference. So again here the a new term came, which is constructive. and the second one is your disruptive. Okay, so it should be constructive interference. Okay, and also it should follow the Bragg's law. So what is Bragg's law? Bragg's law is defined by n lambda equals to 2d sine theta. So this theta is your diffraction angle. Okay, lambda is your wavelength. D is your distance between your interatomic spacing. Okay, so a diffractogram is a plot of the intensity. Okay, so after, suppose let's say you have done this characterization, and after this you want to analyze your material. Okay, so what you will get as a result, in the result you will have a intensity and here 2 theta in x-axis. Okay, so a diffractogram is a plot of intensity. In y-axis it would be intensity of diffracted x-ray at different angles by a sample. So here it would be your angle. Okay, so at what angle your material is giving diffraction. So as per that intensity, sorry, as at that particular angle, you will get the peak like this, and the intensity of this peak would be different, depends on the your materials. So the diffractograms are different from spectra. Components of spectrum are additive. Okay. So here you can see this is the formula of your Bragg's law. So this Bragg's law is very important when you will try to solve some numerical questions. Then this formula is quite often asked. 2d sine theta equals to n lambda, as I have already explained. D is interplanar distance, lambda is your wavelength of incident X-ray, theta is Bragg's angle, n is the order of reflection. So here, suppose let's say you want to put the value of your D. Okay, so this D is different for the different crystal structure. Okay, let's say you have a cubic, you have a triclinic, you have a monoclinic, you have a hexagon. I mean, you have a crystal systems. Okay, so let's say your material and lambda sine theta. So lambda you will know already that what wavelength you are using. Theta you will know that what angle it could be, and D is depend on your, sorry, D is related, depend on the material. Okay, so this is depends on the lattice parameters. So what is lattice parameters? Lattice parameter is HKL, that I have already explained maybe very in the very early of our class. So here if you don't know, then you can also check in the material science, any material science book, the crystal system. So you want to find out the D. So how you are going to find out? So this is the formula for the every material. For cubic it would be 1 upon D square, h square plus k square plus l square divided by a square. Okay, similarly this is for your hexagon. So see here the two different terms came in the hexagon, C and A. So in the hexagon, if you remember, I have explained that time that there will be like this kind of a, okay. So here this distance will be your C. So in the hexagon your C by A ratio would also matter. Okay. So let's see a little bit about this. This I will also explain later. So here you will have in XRD a different filter. Okay. And the detector. So let's say your sample is here. Okay. This is your sample and your ray is coming and it is diffracted. Here it will go, and this is your cathode ray tube. So from the cathode ray tube your X-ray will come. So when your X-ray will come, it has to pass through the filter. Okay, because there is also a wavelength. So for your samples you don't want all the wavelengths, you want some particular. Okay, so by that filter your X-ray will pass and it will incident on the here you can see it is coming to your sample. Okay, so after coming it will diffract. Okay, and this side again your filter will be there, and finally it will be detected by your detector, and that will further analyze, and that will give you a XRD peak at particular at particular angle. So that angle you can define from here. So let's say this angle could be different. I mean 2 theta will be your vary. Okay, because that is instrumental. It depends on the instrument that how much how much angle you want to give, and what is the range of your angle that you want to scan your sample. Okay, so here basically in this course, um, we are dealing with the carbon. Okay, so we have to know the XRD analysis of your carbon. Okay, so the width of the peak, there is two terms. Okay, if you know the full width half maximum. Okay, so what is full width half maximum? It is very important. FWHM. Full width half maximum is what? Suppose let's say it is your peak and it is the top. So it is full width. So this is the full maximum. But we have to take this half maximum. And at this half maximum, we have to take the full width. Okay. So at the half maxima, when you will take the this full width or the width of your peak, this is called full width half maxima, and this is your peak position. So the width is measured at half of the peak height, known as the full width at half maxima. Okay, so there is a very crucial equation which is called the Scherrer equation, and that will give you the crystallite size. So you can also see here B equals to K lambda divided by beta cos theta. So B is your average crystallite size. Okay, so you know the wavelength of your incident X-ray. You know beta is your peak broadening, or just I have explained what is FWHM, full width half maximum. Peak position theta you would already know from this, and K is your safe factor, that is your constant. Okay. So value of this safe factor K is also I mean used for LA calculation. So it is for 0.9 for perfect graphite, 1.84 for perfectly disordered carbon. For LC calculation, if you will use, it is always taken between zero point 0.9 to 1.0. Okay, so it depends because it is a constant. So from this equation, you can find out your crystallite size. So which is nothing but the B equals to K lambda B cos theta. Okay, so okay, now I think we are good to take the questions regarding this numerical that what I have discussed. So I will directly be moving to the question, and that will be solving, and then I'll take the other concepts. Let me just, I think, yeah. So here in this, you can say the value of shift factor K is taken between 0.9 to 1.84 for sp2 carbons. Okay. So this is the constant that you can take in this range for sp2 carbon. Beta is measured from the peak. So for analysis of graphite La and Lc values can be calculated using the Scherrer equation, and Lc is zero point 0.9 lambda by B cos theta, and L is K lambda by B beta cos theta. So this is your Lc and this is your La. Now, so for this diffractogram, calculate D, which is interatomic distance or the interlayer, LA and LC. So for the copper, if mostly what we use is the copper K alpha. So copper K alpha is how much? 1.5406 angstrom. This is the wavelength. Okay. So from this, if you will take, this is your full width, half maximum. So 2 theta is 26.5, 43. Okay. So how much theta would be your 13.25. Okay. So D002 would be your, how much it will, how much it would be? How much? So and lambda equals to 2d sine theta. Okay, so d equals to and lambda divided by 2 sine theta. So when you will put this, then you have to calculate, and here it would be 1.5406 divided by 2 sine, and how much theta would be your 13.25. Okay, so here what you have to do, you have to put n equals to 1 and 1.5406 divided by 2 into sine theta value is your 13.25. Okay, so here how much it will come? It will be 3.36 angstrom. So this is your D002. Again, similarly, you have to calculate for 43. So what would be the theta? Theta will be your 43 by 2. So how much it will come? 21.5. So again, when you will calculate, n lambda, so here 1 into 1.5406, 2 sine 21.5. So how much it will come? 1.5406, 2 sine 21.5. So your D for 100 would be 2.10 angstrom. D100. Okay. So I hope it is clear to you. Similarly, when you want to calculate the LC, okay. So here the formula of your LC. LC was what? LC is here 0.9 lambda by beta cos theta. So here how much your this, as I have said, zero point 0.9 into lambda beta cos theta. Okay, so 8 degree you have to convert into this, so pi by 180, so it will come around 0.139. Now you have to put 0.9, lambda value 1.5406, beta value is there 1.139, and cos theta value is 13.25. So how much it will come? It would come 10.25 angstrom, or you can say a 1 nanometer. LA is also same here. 1.84 would be your K and this, and then beta value. Beta also you have to find out like the similar earlier, and cos 43 by 2. So it would be coming in angstrom around. So is it clear, or should I explain it more? If any doubt, you can ask me question. No question. So we can move ahead. So now, as we are dealing with the carbon material, so in the carbon material, the XRD analysis. So first of all, how you will get to know that your material is carbon or not? So you will get a graphite peak, okay, at 002 plane. At how much angle? At around 26 to 28, you will get one very sharp peak. Okay, this would be a sharp, very sharp, highest intensity. Then you will get a peak at 100, and this peak can be observed 40 between 42 to 43 degree. Other peaks in graphite would also be present. Let's say plane 101, it is around 45, and 004, it is around, it is at around 54 degree, and at 70 you can find 104 plane at 70 degree, and 110 at 77. So 100 sorry 002 peak is observable in all graphitic carbons, with broadening as the disorder increases. Okay, 100 peak, which is your 42 to 43, in most heat treated carbon where only it's present, with a broadening as the disorder increases. The 101, which is at 45 peak, is only observed for the perfect graphite. Okay, so as per IUPAC, if a clear peak for planes can be observed during XRD, a material can be termed graphitic. This does not mean that the material contains perfect graphite crystals. Okay, so here you can see a relative intensity. This is the sharpest and the highest intensity. You will get it around 26 to 28, 002. Then there would be your 100, 101, and 102, and your 004, 103, and 104, 110. So yeah, these are all the peaks that you can obtain in your carbon material. So most commonly the interlayer spacing D between 002 planes of graphite is measured in all the sp2 carbon materials. Okay, so in the case of perfect graphite, the interlayer spacing is 0.335 nanometer. Higher value of the T indicates a turbostatic arrangement, which I have said that what is turbostatic arrangement in the last lecture. Increase in the size of the crystallites can be considered an increase in the extent of graphitization. Typical crystallite size and stack thickness for glass like some and some porous carbon are in 5 to 10 nanometer range. For graphitizing carbon, which I graphitizing carbon means, okay, after graphitizing, which can convert into carbon, generally the values of La increases till 2200 degree centigrade, after which Lc decreases. Okay, so here you can see the graph in this plot is explaining that when you increase the temperature, the La is keeps on increasing, but La keeps on increasing till 2200, after which Lc decrease. Okay, so here you can see Lc is decreasing. I mean, it is getting saturated. Most of the studies are based on powder diffraction. Non-graphitizing carbon samples always behave like a powder due to randomly oriented crystalline. So it is like a non. So this is La and Lc change with the heating for petroleum coke. So here when you increase the temperature, the La will increase and the Lc will also increase. But after some time it will get saturate and it will not increase as La, and this is your crystallite size La and Lc, and this is your temperature. So this is your correlation between La, Lc and temperature. Understood? Is it clear? Okay, so now we have done this XRD. We'll take some more questions at the last that we have collected, but before that, we'll move towards this Raman spectroscopy. So Raman is very common characterization techniques of the material. So basically here, um, you know, the electron which is excited to a higher energy level. Okay, here in this figure you can see due to photons, and it will come back with gain or loss of some energy. Okay, so there will be a Raman effect. As you all know, if you have know the Raman effect, then here what would happen is that, okay, your there will be energy state. So your electron will be excited to the higher energy level due to photons, and it will come back. Okay, after maybe it can come back to the different level, it can come to here or it can come to here, depends on the whether it is losing or the gaining energy. So this is known as the Raman effect. So the all molecules vibrate at all times in different modes. Okay, so there is a frequency is different for the every molecules, the vibration frequency. If any external energy interferes with the vibrational motion. Okay, so in the case of Raman spectroscopy, what is happening there? The photon causes a change in polarizability of the molecule with respect to its vibrational motion, which induce a dipole moment. Okay, so here you can see this is your okay, I will explain this. The scattering in Raman spectroscopy is inelastic because there is a change in energy. Relay scattering is elastic. Okay, so what is, suppose your electron is going to the higher energy level, gaining some energy, and it is going to the higher energy. So inelastic. So inelastic, it means that when it will come to the lower state, then its energy won't be the same. If its energy, so this could be your inelastic. So in the Raman, it is your inelastic scattering. But when it is going and it is coming back to the same, then it is elastic. It is not, okay. So it is elastic scattering because here it is not, losing or gaining energy. So relay scattering is elastic. So here you can see this is your relay. The electron is going and it is again coming back to the same position or the same level. So it is your elastic. This is, it is anti-Stokes Raman. Here it is not elastic, it is inelastic, and here it is also inelastic because here it is gaining energy and here it is losing energy. It is virtual state. It is Stokes Raman, it is anti-Stokes Raman. Okay, so here you can see the excitation layer will come and this is your molecule, and this will have some frequency, so it will match the frequency and only that will pass through here, and there will be diffraction gratings, and this will detect by your detector. So this is nothing but the Raman scattering, and you will get the Raman spectrum peaks like this, something if you have known. Okay, so by the detector, is it clear or any doubt? If you have any doubt, you can ask. I i can answer that. Okay, so now in the Raman of the graphite, if it is your single crystal graphite, the D symmetry with 6 vibrational modes. Okay, there will be a 2E, 2B, and E1U and A2. So E modes are Raman active. Okay, when you will get the peak, there you will find this E 2G band. Okay, so this is Raman active. The first E mode gives a peak at lower wave number at around 42 per centimeter. Second mode is responsible for the G band, which will come at 1581 waves per centimeter. Okay, so this is your G band, which is at 1581 per centimeter. Now you will get a G dash band, or often we called it a 2D band also. So this you would get it around 2724 per centimeter, resulting from a high order 2 photon process. So the electrons gets excited but stays in a real state within the pi band. When it recombines, there is a Stokes or anti-Stokes type scattering. Okay, so the G dash band is also considered a second order of the D band, which I showed just 2D band, we can also say. Hence, sometimes it is called the 2D overtone. In principle, there are minor difference in G dash and 2D peaks. So, although the G band has a strong presence in graphite, it is present in all sp2 sites. Okay, Raman spectra of carbon material generally dominated by sp2 sites because the excitation wavelength used in Raman spectroscopy resonate with the pi state. So you will get this G band at 1581 per centimeter and G dash or 2D at 2724. Okay, so let's say we'll see some questions also. Then we'll discuss this again the next questions. So here you can see the calculating the value of stack thickness for highly disordered carbon, showing the 002 peaks parameter at full width half maxima is given, and this is given, and this. So this it is what stack thickness. Okay, so what is the stack thickness? The stack thickness I have shown you in this slide. Okay, so you have to find this stack thickness. Stack thickness means LC. LC is here, stack thickness. So what is the formula for stack thickness? Point 0.9 lambda divided by beta cos theta. Okay, so here we have to calculate that. Okay, so let's calculate this. Let's solve this problem. So LC equals to K lambda divided by beta cos theta. So K is around 0.9. So you have to put 0.9 multiplied by lambda is 1.5406. Divide by beta is how much given in radian? 0.135 into cos 2 theta is, so it is cos theta, so theta would be how much? If it is 24.8, Okay, 2 theta is your 24.8. So theta would be your 12.4. So cos 12.4. So when you calculate this, how much you will get? So 0.9 into lambda 1.5406 will be how much? 1.38654, and 1.38654 divided by beta is how much? 0.135. Cos of theta is how much? 12.4. Okay, so you have to 0.135 into cos of 12.4. So how much would be your answer? The stack thickness, which is LC, how much? 10.5. I hope it is clear. Clear or any doubt? If you have any doubt, you can ask. Or if you want to know some more questions, then you can also ask. We'll try to solve this. But I hope it is clear. Okay. So the next question is local intensity profile stacks of carbon layer in TM image are generally acquired to understand what crystallized size, layer spacing, intensity of each layer, or the point defect. So it is for the layer spacing, which I will explain now. Let me go to the slides, maybe TM when I will explain after Raman. So let me go to that slide. So firstly, I'll complete this. So here you can see that Raman and IR active vibrational modes are in single layer AV, 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 AV type graphite. So here these are the I mean how it is vibrating. So it is a different band. So Raman spectroscopy can be used for differentiating between single, bi, and multi-layer graphene based on the intensity and sharpness of the G-days band. Okay, so you will suppose your material is a single layer. Okay, let me so you have a material which is single layer or the bilayer or it could be a multi-layer, then the intensity of your G days peak would be difference for the each. Okay, it can be a sharp, it can be a not very sharp, it can be a medium. So it depends. The G days intensity can decide your or it can differentiate that whether your graphene or the material is having or the graphite is a single layer or the bilayer or the multi-layer. Okay, so when you will have a disorder carbons of, or you can, or you let's say you can say a Raman spectrum of disordered carbons. So the Raman spectra of disordered carbons show an additional peak at D band. Okay, so you will get apart from G and G. Okay, this is your G band and this is 2D or the G days. So this is you will get 1581 and this you will get 2720 around. But you will get an additional peak which is at 1350 around. Okay, so this is assigned to the Johm center phonons of this E2G symmetry and K points of phonons asymmetry breathing mode. The position of this band exchange with the excitation wavelength, that is its dispersive. This mode is activated by six membered ring. So here you can see this is six member ring. So this is because D band will come because of this. This is vibrational activated. Okay, so the term D is often connected to disorder. D means what? Disorder or the defect band. Originally this was considered diamond, hence D. So D peak can arise from various types of non-sp2 sites including sp3 sites. The ratio of the intensities of the D and the G peak can typically indicate the change in the graphitic content of the carbon. Okay, so this will give you the graphitic content of your carbon, whether your graphitic is pure or not pure and what is its content. So the Raman spectrum can also be used for the LA calculation, but the methods are crystallite size dependent. Okay, so here that's what in the question it was asking. So crystallite size. The Raman spectrum can be used for LA calculation, but the methods are depends on the crystallite size. Peak integration is challenging and is influenced by the fit parameter. So this is for that. So here in a nutshell, what is this slide is saying about you will get a three peaks. So G and G days is already there, but if there will be a disorder or let's say you can say a defects, then you will get a D band at around 1350 per centimeter. So it is because of the this D band, which is a defect band because of activated by six membered rings. This is so what are these its applications. So here you can see a D band. This is your D band, this is your G band, this is your D 2D or G days. Other low intensity peaks in disorder graphitic carbon. So these are also oh yeah, this is your 2D band, this is your G band, and here you can find out this is D dash, D plus D dash, this is 2D, D plus D dash, and this is your 2D dash. So the Raman spectroscopy can be used for characterizing surface defects. Okay, let's say your material is having a surface defects in carbon fiber doping and or intercalation in carbon. So that will give you a property. Yes. So in Raman spectroscopy is based on a very simple technique. It is, and you will get the spectra also. It looks very simple, but there are still some unanswered questions related to origin of this D and GDES peaks, relationship between this GDES and the 2D peaks, non-linearity of the T peak, and sp2 dominates of the spectra. So there are some questions which are still there, but yeah, in overall it can give you that whether in your material is there any defects is present or not, whether your material is a single layer or the bilayer or the multi-layer. It depends on the intensity of your peaks. So yeah, I mean, this can be give you a overall, I mean, properties of your material. Now, this is very interesting, that electron microscopy. So whenever we go to see after processing or any thing, we have to we are very curious that how our surfaces looks, and how the material is deposited, how our let's say a carbon material, the graphene material, it looks. So because by the naked eyes we can't see the nano or the micro scale level, but when we see it actually in by using a SEM or the TM, we got to know that, oh, whether it is having a flag kind of a structure, whether it is a spherical kind of a shape. So it depends on the material, that what is the size and shape of your particular material. So the de Broglie relations that we all know, which is given by this lambda equals to h by m into v. So where the m is the mass of your particles and v is your velocity and h is your Planck constant, and its value is your 6.63 into 10 is to power minus 34 meter. So if you will know this value and the velocity, or if you know the wavelength, you can calculate the velocity. If you know the velocity, we can calculate that what is the wavelength here using the de Broglie relations. For electron accelerated by, suppose electron in the electron microscopy, we applied some voltage V, then this formula will comes over lambda equals to h upon root 2. Maybe you have done this transformations, or you can see you have seen this formula in your plus 1 or plus 2. So here root over 2 m e into V, where V is your voltage, or it is your electron is accelerated, is your constant. The value is your 1.610 into power minus 19 coulomb, and m is your mass of this, and it is around 9.1 into 10 is to power minus 31 kilogram, and h is again the Planck constant. Okay, so this relationship is valid for low energy electron, as we can neglect the relativistic aspects. But for high energy electrons, after making the relativistic correction, so when you will put the value here, so let's say here you will have this, uh, okay, lambda equals to h upon root over 2 me v. So 1 plus E into V upon 2 mc square. Okay, so when you will have a high energy electron, then the formula of your lambda would come this. So let's say when you will have a electron wavelength for selected accelerator and voltage, so this is giving you the relation. So for the SCM, when you are increasing the voltage, you can use up 1000, 5000, you can use up to 20,000 here, and the lambda would be your this in picometer. This is your 38.76. So when your voltage is increasing, here you can see when your voltage is increasing, this is going to, when your voltage is increasing, then your lambda is going to decrease. So here it is 38, so here you can see a 8.59. Okay, so because here you can see a difference or the, you can say the relation, when the voltage is high, lambda and h is inversely proportional. Here this is your 1, sorry, I will write it in a separate, lambda is inversely proportional to 1 upon root over v. So when your v is increasing, then your lambda is decreasing. So here you can see the increasing of the v and the decreasing of your lambda. So again, in the case of this v, where you are using a, um, 100,000 to here 1 million, so it is also going to decrease your lambda value. And the transmission electron microscopy, as we have seen in the, so transmission electron microscopy, the objective is the same. The only thing, you can get a better resolution and you can fine tune your magnification. You can see a very smaller atomic layer also, or you can see the nano in the nano scales. So, but here the principle is different from your SCM, because here your that is based on your scanning and it is based on your transmission of your electron. So this is a overall setup configurations that you can see. So let's say your this is your electron source, where from where the electron is coming. Then what will be there? You will have a two condenser lenses. So when the electron is coming, it is coming like that. So it will give you the converge. It will converge the electron beam so that it can focus. Okay. After that, this condenser lens again it converges and it has to follow through the aperture. Okay, so if you want to know that why we are using aperture, you can find you can see in the any characterization book, there are a very detailed of this. Then you will have a sample. After passing through this aperture, your electron is transmitting from the sample. Again you will have this objective lens, and you have a selected area aperture and objective aperture. So you will, after this, at last, at all these lenses and apertures, your beam will pass, or the electron will pass, and at last you will have this fence where you can see your morphology of your material. So electron have a much shorter wavelength compared to the x-rays. Okay, so the electrons can be used for getting microstructural information about a material. So that's why we are using in T transmission electron microscopy, so that we can see the morphology, surface morphology of our materials. Okay, any doubt? So after this in TM, very high energy electrons is used because we want to the electron has to transmit within the samples, and it has a setup like a tower like a ship, and the thermodynamic source which is a thermodynamic gun, or let's say you can say a tungsten wire is used from where the electron is coming, or we can say it uh, uh, electron source, and the electron beam is focused using a series of electrostatic and electromagnetic lenses. Now the electron beam is transmits through the samples with some energy loss because it is also inelastic scattering. So the transmitted beam is then detected by is detected, and that can be, and that would be used to generate an image that what we see in our screen. And uh, uh, and in TM, samples must be generally thinner, less than the 20 nanometer, and electrically conductive. That's why it is very important to sample preparation for the TM, because it should be a very thin. So that only you can get a good results. One can also obtain diffraction pattern from this beam, which gives a global information, and also a small section of the samples and image covers, because you can't go through all your samples. So it is in the nanometer scales. So local intensity profiles can also be plotted, and electrons do damage the samples. So yeah, this is all overall view about transmission electron microscopy. So yeah, in TM images of the sp2 hybridized carbon, so the TM images of carbon have been acquired since early 1950s. So the microstructural modes of non-graphitizing carbons have been based on TM of this carbon. So here you can see this is the TM image. Okay, you can clearly see this 5 nanometer scales, and this nanomaterials characterization heavily relies on the TM because you wanted to see the surface morphology. So there are few important aspects like the only edge of the graphenic layers are clearly visible, okay, in the images. So here you can see edges can be clearly visible. Images are 2D projection of the 3D sample. If you will have a 3D sample, then it will give you 2D projection of that, and hence there will be no depth perception. You can't identify the depth of your material. That's why it is only giving a very clear this edge of your graphic layer. So the carbon materials have 60% transparency to low energy electrons. High energy electrons can induce defects and replace atoms in the material. But here the sample preparation can also cause significant stresses, and the heat generated during the process may cause the annealing of defects. So you can find some defects that could be during the sample preparation as well as because of the annealing. So this is the intensity profile, and this is the SAD pattern, selected area diffracted patterns, and this is your TM image that you can of the carbon material. So here the local intensity profile of Stax carbon TM images are generally required to understand the layer spacing, okay, because it's not for the intensity of each layer point defects, so it is for the layer spacing. You can identify the layer spacing because it will give you the graphenic layer, okay, but it is a 3D 2D projection of your 3D images. Now, the two main difference between the vapor deposited diamond and the diamond like carbon are sp3 sp2 ratio and sc by s by c ratio, mechanical property, film thickness, or the diamond crystallite size. So basically here when you will get a vapor deposit, then there will be the sp3 and the sp2 ratio will be different, and also the h by c ratio will also different because the packing system will change in the vapor deposited diamond and the diamond like carbon. So that's why this is the two main difference, which is a sp3 sp2 ratio and the h by c ratio. Now the main difference between CVD graphene and diamond is choice of hydrocarbon precursor, Reynolds number of CVD reactor, pressure inside reactor, presence of atomic hydrogen. So it is quite clear that I have, because of the presence of your atomic hydrogens, there will be the change in your properties of your CVD of graphene, okay, and the diamond because of a presence of the atomic hydrogen in case of CVD. Okay, so that's why that is the main difference, because there is not like a choice of hydrocarbon precursor. This is not a main difference. Now the diamond films are typically grown using PECVD, plasma enhancements PECVD, because plasma enhances the pyrolysis of hydrocarbon. Plasma ensures the high purity of diamond film. Plasma helps generating the atomic hydrogen in such its substrate temperature is low. Plasma enhances the diffusion of carbon species. So basically the plasma, it helps in generating the atomic hydrogen when your substrate temperature is low. So you need not go to the very high temperature in order to generate atomic hydrogen. Then you will be using a plasma enhanced CVD, which we have already seen when we were learning the CVD and the different types of CVD and how the deposition was taking place in different CVD. Which Raman band is used for differentiating between single, bi, and multi-layer graphene? So this is very just similar or the very easy which I have just explained. So there is a single layer, bi-layer, and the multi-layer. So how you will get to know? Okay, so that is given by your G dash peak. Okay, so but G dash is also, you can say the 2D or the G dash, whatever you want to say. So that in when you will get a different here, let's say I can say. You will get a D band, you can get this, or here is your G dash. Okay, this is your G, this is your D. So if you will have a single layer, you can have a bi-layer, you can have a multi-layer. So the intensity of the different of your G dash could be vary. It can be a sharp, it can be medium, it can be small. So it depends on the material, whether it is a bi-layer or the multi-layer or the single layer. So this GDS is mainly responsible for that, and by using this band, you can observe the multiple layer of your graphic. Now, the TM images are the 2D projection of a 3D material. Why? Because okay, so because the entire sample lies within the focal plane. Okay, so here you will have a just you have seen that the electron source will come. You will have a different kind of apertures and the lens, and somewhere your materials will be here. So that here would be your the sample is lies in the focal plane. Okay, that's why when the your electron beam is coming, so that's why it will give you the 2D projection of your 3D material. So that's why you can't see the depth of your material. So that's why you can see the edges but not the depth of your material. It will give you a 2D projection. Okay, and that is because of your sample lies within a focal plane. So that is one reason. Now, the transmission occurs when the wavelength of electromagnetic radiation is what? Is smaller than interatomic distance and almost equal. So, I think when the smaller than the interatomic distance of the material, then only, yeah, interatomic distance of the material, then only the transmission will occur when the wavelength should be the smaller than the distance interatomic. So, here let's say only wavelength should be the smaller than your interatomic distance. Then only your transmission will occur. So this we have seen when we have dealing with the TEM. Which of the following is not currently which of the following is not currently an application of vapor deposited diamonds? So basically we have not seen any vapor deposited diamonds as a battery electrode. So in the battery electrodes, we have not seen any application of this diamonds vapor deposition, but we have seen often using this in your cutting tools or as an optical device coating for automotive parts, but not in the battery electrodes. So one can differentiate between the X-ray diffractogram of a perfect graphite and anneal the non-graphitizing carbon by observing more than okay. So when you will have a non-graphitizing and this, so I think the width of the peaks will vary, position of the peaks and the wavelength of the X-ray, sorry, the number of the peaks. Okay, not wavelength only. You will be varying with your width of the peaks will be different from the graphite and non-graphitizing. Position will also be vary and the number of the peaks can also vary when you will have these two different material. Okay, so let me quickly go through uh, this a surface area measurement. So here you can see this when you will have a porosity in your material, let's say a porous carbon or the activated carbon fiber, the carbon black and other carbon materials with surface modification, patterning or etching. Carbon materials may contain pores in all the dimensions that we have already seen. It can have some open porosity, but this measurement technique can be used by gas absorption isotherms, mercury porosimetry, SCM or the image processing, and the MRI and the micro city, which is X-ray microtomography, is very well known technique. So here this is your material which have a lot of porosity, so this can be used by tomography techniques. So this is your closed pores, this is your open pores kind of, so this is your surface area. Okay. So surface area calculation from isotherms is given by this Langmuir equations and this BET equation, Bernoulli, Amiot, Taylor. So and here these are several methods for calculating the surface area. Okay, and BT is the most commonly used method. Okay, so in the BT is very well known and to know the surface area or the uh, porosity of your material. BT is Bernoulli, Amiot, Taylor. There are various similarities in the terms of different equations. Units are taken accordingly. So yeah, also these are some TM images of sp2 carbons that you can see by yourself how it can be seen here. This is not, you can't see the, it is a 2D projection, not a 3D. So here you can see this 3D 2D image of this 3D. Okay, only edges are visible, not this that the whole depth. So yeah, that's all. Let me know if you will have any other questions. I would take in the next class, and we have seen enough of our questions regarding this lectures. And if you will have any doubt or if you have any numerical problem, please bring it to the next class. We will try to solve that. Okay. So I hope it is clear all the characterization techniques such as XRD and Raman, TEM, and how can be used in order to get our material characterization done.